So 12.3 is on the properties of waves. So we've been looking, okay, we've talked about waves and their characteristics of period, frequency, and amplitude. Let's take a look at the actual properties now. First, we're going to talk about something called a pulse wave versus a periodic wave. We're going to talk about waves as transverse and longitudinal. We're going to be looking at wave speed, frequency, and wavelength. And then we're going to look at energy and amplitude. Okay, it's a pretty quick section. It's not a long one, so we should finish easily on time today for this. First, some definitions, okay? A wave is a simple definition. It's just a disturbance, okay? A motion of a disturbance. So when you hear a sound wave, for example, you're hearing the molecules in the air being disturbed. And those disturbances are propagated to your eardrum, meaning they keep vibrating the other molecules in front of them or next to them until it gets to your eardrum. And then your eardrum is disturbed and it interprets it as a sound. Okay, so that's what you're hearing for that disturbance. The medium, when you've heard medium before, it's not like, low, medium, difficult. The medium is the actual material in which the wave is traveling through. So when you send out sonar waves, what's the medium? What's the medium when you send out sonar waves? What is it?
Water.
Yeah, it's water. Because you're sending out a sound wave in water. That sound wave is being returned to give you a picture of what the surface under the water looks like. That's what sonar is. So the medium would be water. What's the medium in which I'm disturbing waves right now? I'm disturbing particles.
Air.
The air. Okay? The medium, the actual material through which the wave travels or the disturbance travels.
Are we going to deal with stuff that is has more than one medium? Like if it goes through air and water?
Yeah, and we're going to look at how the wave gets refracted. And that's in chapter 14 and 15 with refraction. But yeah, what if it goes through light or through air, then it hits a pane of glass, then it goes into water, the wave bends as it travels through different media. Mechanical waves are waves that require a deformable medium. And the example that's easy is sound. Simply because I'm literally vibrating the molecules in front of my mouth by talking. That's what's happening. So the medium, air, is being deformed. Okay? Can we close the windows a little? Because it's just too loud outside. I'll open the door for some cooler air. Those trucks are really loud. Thanks, guys. Oh, that's much better. Alright. So it requires a medium that can be deformed. Okay, mechanical waves. We're going to see that electromagnetic waves aren't going to be deforming the media which they travel through. Okay, because they're a different type of wave. When we get to EM waves in chapter 14 and 15. Yeah, Marie.
What do you mean when you say that it's deformed?
It is changed. For example, when you speak, you're actually vibrating the molecules. They're being fluctuated, they're moving, they're deforming. Something that deforms can be bent. This paper is deformable. This desk is not deformable while under normal pressure or forces. Okay? A pulse wave. An example of a pulse wave would be like this. If I took something like this piece of rope or whatever it is and just went like this once, it'd be a pulse. A periodic wave would be if somebody sat here and went like this over and over again and it caused it to move. I don't have a rope with me, but a rope would be a good example. Okay, if you have a long rope and you took that rope or a whip, yeah, and you sent a single pulse, right? One quick flick, thank you, of your wrist would be a pulse wave. But a periodic wave would be to continue to do this. And you would see the wave going like this the whole time.
You know when you do it with the slinky and it makes so much noise?
Yeah, with a slinky, that's a good example.
Exercise when they're with the two gigantic ropes and the guys are just
double dutch?
No, not double dutch. No, it's in those they put the rope the really heavy ropes and the guys are just going like that.
You're a double dutch?
I've never seen that, but that's interesting. Yeah, I was gonna say though that does make me think of jump rope as well. The jump rope usually do this. I can imagine he's probably a pro. So the idea of periodic waves is that the source of the waves continues to generate pulses. So a periodic wave is really made up of many pulses. Okay? Again, a pulse wave would be single. Let's talk about transverse and longitudinal now. Okay, there's two different types of waves, transverse and longitudinal. Now, think about, I really need an example here, so let me quickly try and find a slinky.
Double dutch.
Read that real quick. Let me see if there's something in here that I can make a good example. Can I get someone to read first for transverse, please? Transverse. Thanks, Reese.
The vibrations of the particles of the wave move perpendicular to the wave motion.
So perpendicular is the key, and if you take a look at the diagram, what that diagram is trying to show you is different stages of that vibration. Stage A, stage B, stage C, stage D of the rope being vibrated under a periodic wave. So imagine a vibrating blade, that's what that is at the end, okay? With a rope attached to it. And you took the blade and pushed down, let go. And the blade kept going like this. It would generate pulses, right?
A bladicus?
Well, this location right here, this point in space, will vibrate up first, right, in part B, then it'll come back down, then it'll go back down further, and that location of the rope will keep vibrating up and down. So the vibration of the material is up and down, but the wave that's being sent is left to right. That's the perpendicular part of the wave, the perpendicular part. Okay, so again, it's vibrating up and down. You'll see that particle right here, this location, this red dot, is moving up and down, but the wave is being sent this way. So the vibration is up and down, the wave is this way, therefore it's transverse because it's perpendicular to it.
So it's like, it makes a perfect 90-degree. Or
Yeah,
is it
the
just
motion of the particle is up and down,
is it just like
the
a
motion of the
gas?
wave is left to right, so it's 90 degrees. Yeah.
Wait, waves make 90 degrees? Is that what
Again, this, look at the dashed lines, Ev.
you're saying? Yeah.
The direction of the red dot is moving up and down. Look at the red dot. This is part A, part B, part C, part D. It's fluctuating up and down, that location of the rope. But the wave itself is being sent left to right. So the wave is being sent this way. That's that dashed line. The vibrating location is going up and down.
Yeah.
So the vibration is perpendicular to the motion. I'll show you in a moment how it's different when we compress and stretch. Can I get a volunteer to help me out? Somebody want to come up and help? Mike, come on up. Can you grab this end? So, what you're going to notice, and we're going to use another example, compress it a little bit, Mike, so we have some tension in it. There we go. All right, a little more. Keep going, keep going. All right. So, if I send a single pulse, we'll see that pulse, we'll see it return, by the way. We'll talk about how it works in the next section with the return of the wave.
What the heck?
Is that kind of cool to see?
Does it ever stop?
It will, because of damping effect, which is friction, so
Damping?
eventually it would stop. If we send two waves, yeah, you'll see that there's like almost like a sine wave being created. Like keep like keep doing that. No, keep doing that, but try and keep consistent. There you go. Try and get it so that you're moving at the same exact up and down motion.
Ow!
I want you to try and get like a standing wave going on here. Okay, so now watch, everybody.
I see it.
The wave is being sent back and forth between me and Mike, but look at this location. Isn't it moving up and down?
Yeah.
That's a transverse wave, as opposed to, let's put it on the ground so it dampens. All right, lift it back up slowly. All right, don't wave. As opposed to sending a wave like this. Okay? That's going to be a longitudinal in a minute. You see how the vibrations are left to right and the motion is left to right here?
Yeah.
So when I send a wave that way, it's moving back and forth and the vibration is this way. But when Mike did this, the vibration was up and down. This is a standing wave when you get it to continue to look the same the whole time. The vibration is up and down, but the motion is left to right. Okay? Thanks, Mike. We're going to use this again tomorrow to talk about the type of fixtures at the end and how it changes
Can
it.
I have this one?
No.
Would that go
We had one last year and somebody ruined it. We had to get another
down
one.
the stairs?
Would this one go down the stairs? It probably. Oh yeah, it definitely would.
Oh,
It's got a very low K
Let's
value.
build some
Hell
stairs.
All right, let's look at longitudinal just to define it, even though we just talked about it. Oh, actually, really quick before that, take a look at the wave on the top right. We need to look at some terminology. First, from the top and the bottom, you might know these as max and min, right? Max and min from math. The max is also called the crest, and the min is called the trough. Okay? The maximum of the wave that you're going to see is the crest, and the minimum is called the trough. The period when it's on a time x-axis was the length of the wave, really, which is really the wavelength.
The maximum
Right here.
are equal, right?
Yeah. The max and the min are separated from the midline by what's called the amplitude, and they're at equal distances, just one is above and one is below. So the distance from the midline, right here, to the top is the amplitude, or the distance from the midline to the bottom is the amplitude. Okay, those distances are equal when the wave is symmetric. Sometimes you'll have waves that are not symmetric, obviously, and then it wouldn't be equal. Okay, but for a sine or a cosine wave, or a normal wave that we were just looking at there, the top and the bottom were the same or symmetric. The wavelength could be many things. We could think of the wavelength, okay, as the distance from the starting point here. You need to look up to see what I'm saying, by the way. The starting point here to here. Remember, one full cycle there. Or we could think of the wavelength as the distance from crest to crest, or from trough to trough. This distance here is the same as this distance here, which would be the same as this distance right here. Either way you look at it, as long as you complete one cycle, you have one wavelength. And a cycle, when the x-axis or the horizontal axis is time, is called the period of the wavelength versus the actual wavelength itself. Okay, the wavelength is measured in meters. In meters, it's a length, whereas the period of the wave is measured in seconds. The time it takes to complete one of those waves. F.
Can you do from like this, that little baby thing?
Yeah, so you could do from like this node here to this node here. That's fine as well. As long as you complete a full wave.
Oh, so you can't do the first two?
No, because this is a half a wave.
Oh.
You need to go to go through the whole cycle,
So
remember?
make like a whole-
One cycle.
Oh.
One cycle. Or one cycle. Or starting down here.
Okay.
One cycle.
So it can't be crest
Okay.
to trough, it has to be crest to crest to trough.
Yeah, so you're literally completing an upper and a lower cycle both. Or like both half cycles, I should say, okay? And you know how you can tell? Ready? Take a look. If I were to take this portion and this portion and put them together, I would almost get like a circle here if I superimpose them. Okay, that's like a full cycle. Keep that in the back of your mind. So again, the amplitude is the distance from the midline to the crest or trough. The wavelength is the full length of a wave from trough to trough or crest to crest. That's it for this diagram here. Let's take a look at longitudinal now. Okay, longitudinal waves was the example that me and Mike did second, not the first one, where I sent a pulse toward him, and the pulse moved from left to right. The pulse moved from left to right, and you saw the spring kind of compressed, right? When I sent that pulse toward Mike, it was a compression of the spring that was being sent to him, then it came back all the way down this way. Well, if the wave is moving left to right, and the vibration or the compression is left to right, that's what a longitudinal wave is. And it looks as if on this graph here, it's like, well, that's transverse, right? Because it looks like the last one. But what this graph is showing is the compressed nature of the spring. The wave is compressed right here suddenly, and that wave is going to travel. It's going to then be, there's a stretch section here, then it's going to be compressed and stretched again. And that's what you saw when the wave was being sent back and forth. The compressed portion is represented on this graph by the density of the spring. Isn't there a lot of spring right here? And then it's stretched out right here? And then there's a lot of it here, and then it's stretched out again? Where there's a lot, we'd say it has a high density. Where it's stretched out, it would be a little low density. Then again, it is compressed here, high density. Stretched here, the low density. That's what we're looking at on this graph here. These markings line up with these markings right here. So where it's really dense spring, we say the graph is up here. Then it becomes really stretched. It moves down here. Compressed, and then stretched. But the idea that you really want to remember is that a longitudinal wave, the vibrations you're seeing are moving parallel to the wave motion. The motion is left to right, the vibrations are left to right.
So the difference between longitudinal and the other one is, does this one have some parts that are compressed and the other stretched?
The difference, no, between the longitudinal and this is that the longitudinal waves move parallel to the actual motion. Come up again, Mike. I want to show again so we can clear this up. Grab that in. All right, so If we go like this is transverse because the vibrations are up and down, but the wave is actually moving back and forth between Mike and I. Okay? Now, if we don't do that, if I just go like this, do you see how the wave is getting sent left to right? And that wave is a cause of the spring compressing and then moving. That's the second example. The vibrations are left to right, and the motion is left to right of the wave. Whereas in the beginning, the vibrations are up and down, but the motion is clearly left to right. Watch, if I send in a single pulse, the wave moved from me to Mike and then back. So it moved left to right, but it vibrated up and down. That was transverse, because those are perpendicular motions. Whereas if I just simply go like this now, it sends a pulse toward Mike. We need to stop the vibrations. It's not going to work if you have both. You can have both at the same time, and that's going to kind of mess it up a little bit. Okay?
Is there a point
But
where it
this
never stops?
is longitudinal. Because the vibrations are left to right and the motion is left to right. This is transverse, where the vibrations are up and down and the motion is left to right. That's the major difference between these two types of waves. Okay, it doesn't have to do with the compression rate and the being compressed and stretched. It has to do with the fact that the motion of the wave is either parallel or perpendicular. That's why I bolded those. That's the only real difference in these two waves. Ed?
Does it ever stop?
Yeah, so the vibrations will indeed stop, and that's again because of the damping effect because of friction. Okay, because of
No,
friction.
I mean, like when they're going up and down.
Yeah, they're called nodes, where there's no motion. And you notice that when certain times there were locations that weren't moving.
Yeah.
And it was like fluctuating up and down over here and up and down. But in the center, it was stationary.
Yeah.
A stationary point we'll talk about in the next section. Okay? Good point. All right, let's take a look at the speed of a wave. Speed or velocity is defined as displacement over time. Right? Velocity is displacement over time. You know this already. But the displacement the wave travels is called the wavelength. That's this symbol here. Does anybody know what the symbol is called?
Which one? Lambda.
Lambda. Very good. How did you know that? Do you mind me asking?
Half-life 1 and 2.
Ah, awesome. Lambda, half-life. So here, the symbol is called lambda. The easy way to draw it is with two lines like that, and it represents the wavelength. We wrote that on the last slide. Okay, but let's write it again, and it's measured in units of meters. So the displacement x is really the wavelength, because we're looking at a wave now. The time it takes t is really the period, tau. But remember that the period is defined as 1 over the frequency. Okay, the period is really defined as 1 over the frequency. Well, what do you do when you divide by a fraction? You really multiply by the
1.
reciprocal. So if I take lambda divided by the fraction 1 over omega, it really means lambda times the fraction omega over 1. Again, when you divide by the fraction 1 over omega, it's the same thing as multiplying by omega over 1. The period is tau. That's the frequency. The frequency. The period is tau. The frequency is omega. From the last section, we talked about how tau equals 1 over omega. So we're replacing tau with 1 over omega. Now, we're dividing lambda by the quantity 1 over omega. When you divide by a fraction, you multiply by the reciprocal. And therefore, it becomes lambda times omega all over 1. Or simply lambda times omega. Okay, this is where it comes from. What you need to remember, or what you're given on your formula sheet, is what's in that box at the end. Okay, so this is what you are given right here, boxed in. But where it comes from, okay, this is where it comes from right here. This is the derivation of it. But the part that you're going to remember or know how to use is this portion here. And what this tells me is that the velocity of any given wave is the product of its frequency and wavelength. So if the frequency is really high, the wavelength is low. And we're going to see that with the electromagnetic spectrum in the next few units. Okay, but again, this is the portion we need to know. But it'll be given on your formula sheet. Okay, what are the units for frequency?
Hertz.
Hertz. Yeah, hertz. So you end up getting meters for the wavelength and hertz for the frequency. Those are the units there. Again, hertz times meters. Hertz times meters, which sounds kind of weird. But hertz is defined as 1 over second. So my units become 1 over second times meter. Well, what's 1 over second times meter?
Meters over second.
Meters over second. What's a meter per second really though? What unit or what variable have you always said all year?
Velocity.
Velocity. And that's what we're looking for. Velocity.
So what do we put for the unit?
Okay?
The unit.
For velocity?
No, it's like, if it's like, oh, never mind. You don't really need units, right?
I'm just showing you the breakdown, but the units of frequency are hertz. The units of wavelength are meters. The units of velocity are meters per second. Okay? The same units we've always used, but to show you where the meters per second is true, if you redefine hertz as 1 over second, okay, it becomes meters per second. Because again, it's velocity. So example 1 says the wavelength of a sound wave produced by a middle C on a trumpet. Okay, a middle C on a trumpet is approximately 0.72 meters. That's the actual wavelength. So the length of the wave that you hear is actually this long. Okay, say a meter is here, 0.72 meters, about this long. That's the actual length of the wave produced by a middle C. Which is kind of amazing to think about, that your brain is interpreting that long wavelength. If the speed of sound, not sounds, if the speed of sound in air is 343 meters per second, which is the actual speed of sound, calculate the frequency of this note. And remember that frequency is really the pitch. The pitch. So we know several things. Okay, here's our wavelength. Here's our velocity. And all we're trying to do is find the actual frequency. So this is a simple calculation. You're going to plug into the previous formula we just used. And you could solve for omega. Okay, so omega equals V over lambda. If we solve for omega there, just divide by lambda on both sides. So you get, 343, not 34, sorry. 343 over 0.72.
So which one do we use?
What do you mean?
Use the formula.
V equals W.
You're always using this formula. That's what I said, Ev. Always using this formula. Okay, this is where it comes from. This is where all the work comes from. But you don't
Yeah.
need to memorize that. You're using that formula. Okay, and look at the problem. The problem gives us wavelength. You got to keep up. You're falling behind. That's why. Come on. Yeah. It gives us wavelength. It gives us velocity. We have velocity, wavelength. We're trying to find the frequency, so we solve for omega. These are just plug and chug, these ones, guys. Please look at your units. Write down your givens. I think it was around 470 and change. So let's see. Yeah, 476 will approximate. 0.4 you get? 0.4? That sounds right. What are the units of frequency? Hertz. Okay, so if you had a tuner, okay, for those that like music, ever used a tuner before? The tuner gives you a frequency. Okay, it's measured in hertz. So if you were flat, if your sound was flat, it would be a little less than 476 hertz. If you were a little bit sharp, if your instrument wasn't tuned correctly, and you have to change that slide valve on the trumpet to change the length of the wave which it's traveling, you're changing the pitch again. If you're sharp, it would be above this frequency. That's what you're measuring when you're what's it called again? Tuner, sorry. When you use your tuner for your musical instrument.
There's like a $300 tuner app on for like the iPad.
That's a waste of money.
Yeah.
You can buy a tuner for like $20. So what? Ah, there you go. I would imagine it would be free, obviously.
I was just looking up like iPad apps.
I was trying to find a decibel level measurement app for the pep rally competition. Remember who was louder? there's a decibel measuring app that you can use, but in the gym I got no service. Or else I was going to give Mr. Tio so he could use the app and see which grade was actually the loudest. Remember they were measuring the loudest? That's a decibel level measurement, which is really measuring the amplitude of the wave, the amplitude level.
The loudest.
That's what they do in Seattle, right, with the stadium, yeah.
The stadium meters?
They call
I'm sure they do, but sometimes I don't know if they're real or not.
Seattle had, like, the actual professionals coming, because they're, like, in
Oh.
the stadium.
They cause an earthquake.
Yeah.
After after Marshawn Lynch scored a touchdown and like a championship.
Cause the minor earthquake?
Yeah,
I could see that because an earthquake is a vibration of the plates. Sound is vibrations. When I went to Villanova in the pavilion is one of the smallest basketball arenas in the country, but it has the largest volume density in the whole country of all NCAA. Because it's so small and they pack so many people into it that the volume, the density, not the actual sound, the decibel level was not louder than other places, but because of the amount of small volume, the decibel level per unit volume was the largest in any stadium in the entire country. Because there's so many people packed into a small area that are so loud that the density is the loudest. The sound itself is not the loudest, but it feels like it because you're all in a small volume. Okay? Let's go. The second example says to calculate the wavelength of an X-ray, which is a type of EM wave of an X-ray, if its frequency is 3 times 10 to the 12 megahertz, units we have to change, and the speed of all EM waves is 3 times 10 to the 8 meters per second, also known as the speed of light. Many of you know that. Okay, you've seen that before, but that's where the speed of light comes in. The light is an EM wave. So let's list what we know. The frequency we start with. 3 times 10 to the 12 megahertz. Anybody remember what the prefix mega means? Times 10 to the
1,000.
times, what is it? 6. Very good. Times 10 to the 6. So really what this is the following. It's really 3 times 10 to the 12 times 10 to the 6 hertz. Again, on your computer, a megabyte is a byte times 10 to the 6. A kilobyte is a byte times 10 to the 3rd. Just like a kilometer is a meter times 10 to the 3rd. Mega is times 10 to the 6. So how many really is this? Times 10 to the 18 hertz. Okay, that's the frequency we need to use for this problem. So when you see mega, and you're going to see mega a lot with frequencies. Your radio station, 100.3, is measured in megahertz. So it's really 100.3 times 10 to the 6 hertz. But they're not going to write times 10 to the 6 on the radio station, so they write megahertz as the unit at the end. Okay? So 3 times 10 to the 18 hertz. Next, the velocity, or in this case the speed, okay, is 3 times 10 to the 8 meters per second. So let's find the wavelength of an X-ray. Here's our formula. Again, the same formula. And now we're just solving for lambda. We're looking for the wavelength now. So we divide by omega on both sides, getting lambda by itself. So velocity over omega equals lambda. Okay, so 3 times 10 to the 8th meters per second all over 3 times 10 to the 18th hertz. You're going to get a very small number because you're taking a very, very small number, relatively speaking, over a much larger number. Okay? What do you get, Maria?
1 times negative 10 to the negative 10.
Yes. And the units are going to be meters because it's wavelength, and you can see that because hertz is really 1 over second, and the seconds cancel there. Okay, hertz is really 1 over second. Seconds cancel, leaving behind the meters up top. These are our units right here. Now, to give you a little idea of what this really means, 10 to the negative 9 is a nano, if you remember that. So if I convert this to nano, it would be 1 times 10 to the negative 1 nanometers. Okay? A nanometer. Ever hear of nanotechnology before? Nano is a small scale. Okay, 1 times 10 to the 1 nanometers. That means we're looking at like 0.1 nanometers. The waves are so small, that's what allows X-rays to penetrate your body. How do you think that's happening, right? When you get an x-ray and they measure your bone to see if it's broken or not, they're using the densities for a lot of it, but those x-rays are so small. That's how they're able to get through your body to actually give you a reading or give you a printout of your bone structure, whether it's broken or not. You put those lead things on to stop the nano waves, in a sense, from getting through you, because lead is very dense. It's not able to penetrate lead. Yeah?
How can it still show the picture even with the lead thing? Because it's only covering part. Lead doesn't kind of like do it.
Usually the lead part you put on doesn't show the picture.
No, that's right. How does it, like, how can
It stops the nano wave from getting through. The molecules are so close in the lead that it doesn't allow the wave to travel through it, as opposed to your body, which the wave can travel into because it's a small wave.
What happens if they get through?
Could you die?
It's not gonna, it's made out of lead. Too much would hurt you, that's the idea. And certain internal organs
Could you die?
are more, I guess, susceptible. I'm not a bio person, I don't know too much about that part.
So if you got X-ray everywhere, could you
Enough radiation could hurt you, but it's not going to kill you. And like if you go in for one thing and they were to forget to put the thing on you, okay, the lead, whatever it is. Why don't you wait a minute? I want you to see the other problems. Okay. Okay. The third part of the notes. The third part of the notes talks about wave and energy here. And here's the way this works. Okay, waves transfer energy. They transfer energy by transferring the motion itself rather than the matter itself. So when Mike and I were moving the slinky up and down, the actual slinky, the matter itself wasn't moving. But the motion was being transferred from one person to the other. And that's the energy that you're transferring. And if you have more energy, you had more amplitude. Notice when I went like this, the amplitude of the wave got higher, didn't it? Got much higher up. So what we can say is that the amount of energy, okay, is usually proportional to the amplitude of the wave, but it happens to be proportional to the square of the amplitude.
What is that thing you
Okay,
made?
proportional to. So the amount of energy in the wave is proportional to the amplitude of the wave squared, or the square of the amplitude. The square of the amplitude.
You got 1 minute.
Okay, thank you. Just trying to find the time on there.
What are brain waves?
Now, hold on. I want to get through this before I take questions. There's a lot to talk about. Still, we have a minute. So, this explains why if you release a mass that's hooked to a spring, it will start to oscillate. But over time, it will settle out. Because it's losing energy to friction. And if it loses energy, it loses amplitude. So you'll notice the mass, instead of oscillating like this forever, will eventually settle out. The amplitude is decreasing because it's losing energy. Okay? Tonight, make sure you take a look at the homework from this section. That was the last thing I wanted to talk about here. Okay? That effect that we just talked about is called damping. A damping effect. What causes it to stop oscillating.
Does gravity stop